Okay, so what we will be discussing today is is mostly about ideal Bose gas. So in the last class, what we saw is that depending on how your wave functions are, the occupation number changes, which means that how a particular type of particles would be distributed in a given system, given some energy levels or some spectrum of single particle states, how different particles will be distributed. In the quantum regime, what happens is depending on the type of particles or the type of wave function the particles are represented by, they have different kinds of occupation number. So they get distributed in this energy levels or the single particle states differently. And depending on that, we get different characteristics. Okay. So mostly we studied about, on one end, we have the distinguishable particles where we can have the Maxwell-Boltzmann distribution, but then we can have indistinguishable particles. And there, when the wave functions of the particles are symmetric, we can get bosons which would have some occupation number where you can have all. So there's no control or no you can say no limit on the number of particles being in one particular state. While on the other hand, if the particles are fermions, which are actually they are represented by as antisymmetric wave functions, so there they can have only you can have only one fermion in one single particle state or no fermion. So that's how the occupation number is different, or the distribution of fermions and bosons are different given a particular spectrum of single particle states. And we had discussed about Fermi gas in the last class. So what we will do today is we will try to see the characteristics and the properties that come out of bosons. So we'll study about the ideal Bose gas. Okay. So, as we always do, we will first discuss, we'll mostly in this class, we'll mostly discuss about the properties and how, what are the different ways of defining the different thermodynamic parameters and what they tell us about the system. So, an important or interesting property of Bose gas is the Bose-Einstein condensation, which does not happen in Fermi gas or in other systems. So we'll read about that. So we'll discuss all these basic concepts, and then we will discuss some questions. Okay, and please get back to me if you have some doubts. Okay, so first we'll recap what we had done in the last class, because there were certain things which were general, and then we had discussed about the Fermi gas. So I'll recap about that general things, and then we will go into Bose gas today. Okay, so consider you have some ideal gas in quantum mechanical canonical ensemble. Okay, so by ideal gas you should remember that then we are not considering any interparticle interactions between the particles. Okay, so for an ideal gas in a canonical ensemble, we know that we can write the canonical partition function given by summation over e to the power minus beta e, where e is denotes the different eigenvalues. Okay, and then if ne is the number of particles in single particle energy state epsilon, so single particle energy states are represented by epsilon, and there are n epsilon number of particles in such states. So then the total energy E is given by summation over epsilon n epsilon, and then summation over all the different number of n epsilon will total give you the total number of particles. Okay. And here, what's interesting is that now, depending on the type of particles that we have, we can assign some statistical weight factor there. So if you have Maxwell-Boltzmann distribution where the particles are distinguishable, in that case, we have this statistical weight factor, which is given as a product of over all the epsilon values, 1 by n epsilon factorial, right? So this comes from the fact that if you have some given distribution set represented by n epsilon, and then so which means n1 particles in some state, n2 particles in some other energy state, then how many ways is this distribution possible? It's given as capital N factorial by product over all the different ni factorials. And then considering the Gibbs factor, we ultimately get this statistical weight factor. This is something we had discussed in the last class. But then what we are focusing on today is indistinguishable particles. So there the numbering of the particles doesn't matter and the particles are indistinguishable. So in that case, what happens is the statistical weight factor comes out to be 1, right? So here you should remember that the G that I have specified here is actually the statistical weight factor and it's not the degeneracy. Okay. So now that was for the canonical partition function. But if you go to grand canonical partition function, so there the only difference between Bose-Einstein and the Fermi-Dirac case comes because of the allowed values of Ni, right? And weight factor that was represented by G in the last slide is 1 for both the cases, because for both cases the particles are distinguishable, right? So now uh, this is how the grand canonical partition function is defined. So here Z is the fugacity, which is given as e to the power mu by kT, where mu is the chemical potential, right? So now you can see there are two summations. One is summation over n, and then we have summation over the different distribution sets, right? So this is just using the properties of exponents. We can write this summation, we can change this summation to a product, okay? So this double summation that we see here, so there is a summation over the number n epsilon constrained by some fixed value of n. And then we consider that even n can be varied because now it's a grand canonical ensemble, right? So what can be done is we can do one, so that can be equivalent to one summation over all possible values of n epsilon, right? Independent of each other. So that means we can write Q. So Q is the grand canonical partition function, and you can write it as summation over different values of Ni, like N0, N1, dot, dot, dot. And then you have these terms, right? So these are all products. So you can write it in terms of these products. So you are summing over all possible values of each Ni's, right? And now this is a general case. Now, depending on whether you have Bose gas or Fermi gas, your possible values of Ni, or like each of this N0, N1, N2, each of these values, the possible values will be different. So for Bose gas, you can have any value of Ni, while for Fermi gas, you just have two values. One is 0, another is 1, right? So what we will now do is that if you put those values, then you get this expression for the grand canonical partition function, right? So this tells you that for this to be defined, Z e to the power minus beta epsilon should be less than 1. And this is an important relation because this in a way tells you that the chemical potential should be less than the energy levels or the single particle energy states that are possible or that are present in the spectrum for your given system, right? Now, this is your grand canonical partition function, okay? So you can find the Q potential from here, which is given as ln capital Q, okay? And this has a value like this, and that is equal to PV by KT. This comes from the analysis of grand canonical ensemble, which we had already done in the previous classes when we discussed about grand canonical ensemble, right? So now what we can then do is that, see, now you have this PV and KT. So PV by KT, that means in a way you can use this to find the different thermodynamic parameters or for finding the equation of state. Okay. And if you generalize for all the cases, you would get something like this, well, where A is -1 for Bose gas, +1 for fermions, and 0 for the Maxwell-Boltzmann case, right? So for our case in today's lecture, we would we would put the value of A as -1 and we would try to solve for the Bose gas. Okay, right. So, and then we know that this is how your mean, or you can say the mean number of particles or the mean energy or the average energy can be defined. Okay, and there, so this has its basic definition is this, and then you can write this in terms of this derivative of the Q potential. And this in a way tells you that now you can write n as summation over epsilon, the mean of n epsilon, and this is called the mean occupation number. Okay. And this is given by this expression here. So depending on the value of A, you can have the mean occupation number for the different kinds of particles. And if you plot n epsilon, mean occupation number, you would get something like this. So where you can see that for fermions, it's always less than 1, and this is how it goes. While for Maxwell-Boltzmann, you can see that for where mu is close to epsilon, okay, there you can see that it blows up. And this tells us something, okay? So we will see what this tells us is that, so the mean occupation number blowing up means that there are a large number of particles at this state, okay? And this refers to some kind of condensation, which is called the Bose-Einstein condensation, which we will read read about in the coming slides, okay? And then this is for the Maxwell-Boltzmann case, right? So now, till now, what did we discuss? We discussed about how the you can say the grand canonical partition function looks like for Bose gas. Okay, how we can write PV by KT in terms of in terms of the grand canonical partition function. Okay, and then how does the mean occupation number looks like? And then now we'll use this information. We'll use it to see or use it to study the thermodynamic properties of ideal Bose gas. Okay. So before doing that, what's interesting to note is that, so we can have some system, but what will tell us whether the quantum effects are relevant for our system or not? Okay. So that's an interesting thing. So under what limit will a system uh, show classical behavior, or will tend towards the classical behavior, and under what conditions the quantum effects are very prominent and one needs to consider the quantum effects, right? So there should be something which defines this limit. And so that is what is defined by this term n lambda q, right? So we will see that we will investigate in details the physical behavior of a class of systems in which, while the intermolecular interactions are negligible, okay, because we are all dealing with ideal gases, but then the effects of quantum statistics assumes a very important role. And under what condition does it play an important role, and where can we consider it to be close to the classical limit? So that means that the temperature and the particle density. So we know that the when a system is at a high temperature, or when the density of the particles are too small, so under those cases it behaves like a classical case, right? So that means in those cases n lambda cube is much less than 1. But when this is no longer the case, so when T and N no longer conform to this criteria, that is n lambda cube less than 1 is no longer true, where lambda is the mean thermal wavelength, or the thermal de Broglie wavelength of the particles. So under that condition, the quantum nature comes into effect. Okay. In fact, the quantity n lambda cube turns out to be a very appropriate parameter in terms of which the various physical properties of the system can be adequately expressed. So the limit when n lambda cube tends to 0, all physical properties, they generally go towards the classical counterparts. Okay. And for small but non-negligible values of n lambda cube, the various quantities pertaining to the system can be expanded as power series. And from these expansions, one obtains the first glimpse of the departure from classical limit. So so gradually when n lambda cube becomes non-zero, the quantum effects set in. Okay. And when n lambda cube becomes close to unity, or becomes of the order of unity, the behavior of the system becomes significantly different from the classical one, and then it is characterized by quantum effects. So this value here in a way tells you whether you are in the classical limit or in the quantum limit. Okay. So that means when you are at lower temperatures, or when the number of particles or the number density is huge, so under those conditions, quantum effects would set in, right? Okay. So now we would deal about the ideal Bose gas. Okay. So if you put the value of A in the last expression that we had derived, the general expression, there was an A there. And now if you put A equal to -1, which is the case for the ideal Bose gas, you would get something like this, right? So now here capital Q is the grand canonical partition function. So this has a summation, as you can see. And then if you have a large volume, or if you consider that your single particle energy states have a are actually continuous. In those cases, you can change it to an integral. Okay. And similarly, you can define n as summation over epsilon, so summation over the mean occupation number, and that is given by this expression here. So here you have put the value of a as -1, right? So what's important to note here is that for Bose gas, z e to the power minus beta epsilon is less than 1. So you know that z is equal to e to the power mu by kt, right? So in a way, this tells you that mu should be less than epsilon, right? So, which implies that the chemical potential must be lower than the ground state energy. So, if you're suppose for free particles where free massive particles, so where you can define the energy as p square by 2m. So, there the zero momentum state or where the energy is zero. So, in that case, the ground state energy is given as zero, right? So, in those cases, mu would be less than zero. Okay. And if you consider this value, so you know z is equal to e to the power mu by kt. So in a way that limits your value of z from 0 to 1, right? So we will see under what limit, what does it physically signify. But z values do remain between 0 to 1. Okay. Now, if you have large V, considering that the spectrum of single particle states are continuous, we can move from summation to integration, right? So this summation can be replaced by integration. And how will we do that? We have done it in the last class as well, and we will do it again here. So, this is your expression, right? This is a general expression with A. And here you have replaced A by -1, okay? Now, how do you change it to an integral? You change it to an integral by doing an integration over the phase space. Okay, so integration over all values of momentum and coordinate. And then, as you can see, if your energy is not dependent on the position, and if it is just a function of momentum, you can take the integration over the coordinates outside. So then what happens is you have a v here, and you get another v which gets cancelled. So in a way, you can write p is equal to kt by a, and then this integration where now you can see that you have changed to the spherical polar coordinates, where you have written uh, so d3p is now written as 4 pi p squared dp, right? So you have changed to the polar coordinates, and this is how it looks like. And then if you do the integration, you'll see that this term goes to 0. So what remains is this. So this is how you define P, or the pressure. Now, depending on how your energy depends on your momentum, you can have different expression for the pressure, and then you can solve it to get the pressure, right? Now, for Bose gas, A would be replaced by -1. Now consider that you have non-relativistic free particles where energy is given as p square by 2m. So if you do this substitution, you can define a density of states which is given as a epsilon d epsilon uh, equal to 2 pi v by h cube 2m to the power 3 by 2 epsilon to the power half d epsilon, right? So how do you see that? It's just that here, if you replace now with, so replace p and dEdP using this relation, you would get this following density of states. So it's important to note here that in 3 dimension, when you have your system is in 3D, you are doing an integration over the entire volume, and there what you get is that the density of states depends on energy as e to the power half. Okay, this won't be the case if you have a 2-dimensional system or a 1-dimensional system, because then this integration, so you won't, at that point you won't have a 4 pi p squared dp term, right? So if it was in 2D, you would have had a term like 2 pi p dp, right? So that means depending on that, your final power of energy, okay, final power or exponent of energy that you get in the density of state differs, right? So in 2D, you can see that it would be independent of energy, while in 1D, you would get a dependence of e to the power epsilon to the power minus half. So depending on the dimensions of your system, your density of states can differ. So for 3D, this is your density of states, where you have just changed from the momentum space to the energy coordinates, okay? So what we now note here is that What this tells you, so the density of states is proportional to epsilon to the power half, where epsilon is the single particle energy state. So this tells you that there is zero state, or so the density of states is zero when epsilon goes to zero, right? So that tells you that there are no particles in the zero state. But this is wrong, because in quantum mechanical treatment, we must give a statistical weight, okay, to each non-degenerate single particle state, because you do have a state with energy zero, but what this is telling you is that there are no particles there. Okay, so in a way, this density of states does not take into consideration the number of particles that can be present in the zero state, right? So what we have to then do is that when we do the integration, or when we replace the summation by the integration, there we have to take the epsilon equal to zero case explicitly outside. Okay, so what we then do is that, so this is your last term, same as what we had done in the last slide. But then now you have this extra minus 1 by V ln 1 by Z, 1 minus Z term. So this comes by putting epsilon equal to 0. So we explicitly write this term, right? And similarly for N, we have this 1 by V Z by 1 minus Z term, right? So now one can ask a question that why didn't we do this for fermions? Why are we specifically doing it for bosons? If you remember, for fermions, we just directly used this density of states and we directly did the integration. We did not consider the epsilon equal to 0 case explicitly outside the integral, right? So this is because of the characteristics of the Bose gas, which allows us to have all the particles in the zero state, which is possible. Like in for some values of temperature, or given some value, given some condition, one can have a huge number of particles or large number of particles in the zero state. Okay, so by ignoring the energy, by ignoring the density of states in the zero level, you are ignoring a significant, uh, you can say, significant possibility of some new behavior of the system. But in fermions, you can have only one or no particle in each energy level. So there you, if you ignore this term, you are just ignoring one particle, one single particle state, right? So that doesn't matter much. But because you can have, there can be situations where you can have huge number of particles in the zero state for bosons, we are not in a position to ignore or neglect this epsilon equal to 0 energy level, right? So for this is the reason why for bosons, we have to explicitly have this epsilon equal to 0 term. Okay. So now for Z much less than 1, which corresponds to situations not far removed from the classical limit, each of these terms is of the order of 1 by n, right? And therefore negligible, okay? However, as Z increases and assumes values close to unity, what happens is that this Z by 1 minus Z into V, which is equal to n naught by V, n naught being the number of particles in the ground state, can become a significant fraction, okay, of the quantity n by V. So that means when epsilon gradually goes, you can say, goes close to 1, there you can't ignore this term, right? This term becomes very significant in those cases, right? So one thing you have to note that here Z by 1 by Z, Z by 1 minus Z is replaced by n naught. Why is it so? Because now if you go back and look at the expression, the, you can say, the mean occupation number, maybe, okay, you would also have that expression here. So maybe you look at the mean occupation number here. So what happens when you put epsilon equal to 0? What you get is 1 by, just look at the mean occupation number. Don't consider this summation now. We are just looking at the mean occupation number. And that is given as 1 by Z inverse e to the power beta epsilon minus 1. Now, when you put epsilon equal to 0, what you get is 1 by Z inverse minus 1, right? That is equal to 1 by Z minus 1, right? And that is also equal to Z by 1 minus Z, right? And that is what you have here, Z by 1 minus Z, right? So That means Z by 1 minus Z is the value of the mean occupation number when epsilon equal to 0. And what does mean occupation number tell you? It tells you the number of particles that are there in that state, right? The average number of particles in that state. So that means Z by 1 minus Z can be replaced by N naught, which is N naught where N naught is the number of particles in the ground state, right? So that's how you can replace this term as N naught by V. Okay, and this term becomes quite significant as Z tends to 1. Okay, gradually as Z increases. And then what you see is that, so that means gradually as Z tends to 1, you would see that Z by 1 minus Z, this would gradually tend towards N. So you would have N by V. Okay, so this accumulation of macroscopic fraction of particles into a single state of epsilon equal to 0 leads to the phenomenon of Bose-Einstein condensation. Okay, and this is what makes it very different from the fermions, where you could just have only one particle in each energy states. Okay, here you can there can be situation where you have almost all particles in the zero energy state. Okay, and that is the situation where we call it as a Bose-Einstein condensation. Okay, so now this is an expression for the P by KT. This is the expression for N by V. And now what you can do is you can solve for this. So another thing here is that in the limit, you can see that this goes as 1 by N. Okay, so you can ignore this term, but then this cannot be ignored as Z tends to 1. Okay, so this is your expression for P by KT. And then what you do is you define this integral. So you define a Bose-Einstein function, which is given as g nu of Z. Okay, and this is how it's defined. And then if you replace it in the integral, you can write an expression for the pressure. You can also write an expression for the number of particles. Okay, so here you can see that you have taken that N naught by V term on the left hand side. So you get N minus N naught by V equal to this integral. Okay, so this is this G 3 by 2 or G by 5 by 2. These are the different Bose-Einstein functions. Okay. Now, once you have done that, you can also find the internal energy, and that is given as minus del del beta of ln q, where q is the grand canonical potential function, grand canonical partition function, right? So now what you can do is you can this derivative over beta is again replaced as by derivative over temperature. So it's just a substitution. Okay, considering beta to be 1 by kt, and this is what you get, right? Now, if you look at the expression for lambda, you can see that lambda goes as t to the power half. So if you use this relation, finally you get this expression for the internal energy, and you can further use this expression to find the specific heat. Okay, and you can also match uh, with this relation which we had initially derived in the last class, that for massive particles or the particles where you can define the energies as p square by 2m, their pressure and energy has this dependence given as p equal to 2 by 3 u by v, right? For massless particles, it's given as 1/3 u by v. So this also matches with what we had done in the last class. Okay, so all these things are consistent. This shows that it's consistent. Okay. Now, if you look closely in this expression, so N naught was the number of particles which was in the ground state, right? And then N is the total, okay, and N is the total number of particles. So that means N minus N naught in a way tells you the number of particles that are in the excited state, okay? So if you define that as NE, N subscript E, then you can write it as NE by V equal to 1 by lambda q g3 by 2 z, right? Now, here what they have done is they have written explicitly the expression for the mean thermal wavelength. Okay. So Ne is the number of particles in the excited state. So that means in the state where epsilon is not equal to 0. Okay. And unless Z gets extremely close to unity, what happens is N epsilon is, so it's close to N. So because it is obvious that for Z ranging from 0 to 1, the function G 3 by 2 Z increases monotonically with Z and is bounded. Because see, if you look at the expression for Z, this is how your G is defined, right? G is a series of Z. And then if Z has a limit, Z has an upper bound of 1, G nu of Z should also have an upper bound when Z is taken as 1, right? So that means now if G 3 by 2 Z has an upper bound, which happens when Z is equal to 1, you can tell that the number Ne, or the number of particles in the excited state, also has an upper bound, right? So this upper bound of G 3 by 2 is given as this expression here. So it's close to 2.612. Okay. Now, hence, for all Z of interest, you can say that this is how it goes. So this value is bounded. That in a way tells you that Ne is bounded. Okay. So given some value of volume and temperature, the total number of particles in all the excited states taken together is also bounded. And this is given by this expression here, right? So now you have to consider that you had n number of particles, okay? And out of that, n naught is the number of particles in the ground state. Ne is the number of particles in all the excited state, okay? Total number of particles in the excited states. And you are told that the number of particles in the excited state has a bound, okay? It has a limit. So given some value of n, two cases can now arise, okay? So what happens when n is less than Ne? Okay. So when n is less than Ne, all particles are distributed over the excited states. Why? Because you have still not reached the limit of Ne. So the particles would go and distribute in the different excited states, right? So everything is fine. So all particles are distributed over the different excited states. So in a way, you can say that Ne is approximately equal to n. But then when n, that is the total number of particles, is larger than Ne, you have a limit to what your Ne value can be, right? So whatever value is extra, so all the extra number of particles would then go to the ground state, right? So you can say that Ne in that case would be given as this value. This is the maximum value of Ne that can be possible, okay, for a given value of V and T. And then whatever remains, so n minus this value would go to the ground state, okay? And if you use this relation, you can write Z as 1 minus 1 by n naught. So this in a way tells you that this is what happens when you gradually go close to unity, right? So that means when n is much less than n e, or when you can say the total number of particles are much less than this bound over the excited or bound over Ne, you can write that Ne is close to n, or Ne is approximately equal to n. But when n becomes larger than Ne, there you have a finite number of particles in the ground state, okay? And there you can no longer write Ne being approximately equal to n, okay? So this is what is being told here, that unless Z gets extremely close to unity. So when Z gets extremely close to unity, this is the case when n is much greater than Ne, okay? So if Z gets very close to unity, Ne is no longer approximated, or Ne cannot be approximated as n, because n naught is quite significant there. But otherwise, when Z is much less than 1, in those cases, you can always approximately replace Ne by n. Okay. So these are the two cases depending on how many number of particles are there in the system and what is your volume and temperature of the system that is given, right? So this knowledge, whatever we are discussing now, can be now extended to understand what happens when we say that there is Bose-Einstein condensation that is happening. So this is what we just discussed, right? So now Z for all practical purposes is then unity, right? When n is much great, or when n is greater than n epsilon, ne, right? This phenomenon of a macroscopically large number of particles accumulating in the single quantum state, which is epsilon equal to 0, right, is generally referred to as the phenomenon of Bose-Einstein condensation. Because Z going close to 1 is the case when you have large number of particles in the zeroth state. Okay. And this is what happens when the number of particles are greater than Ne. This is called Bose-Einstein condensation. So in a certain sense, this phenomenon is akin to the familiar process of vapor condensing into a liquid state. Okay. But there is a difference, a very important difference. So when we talk about condensation, vapor condensing into the liquid phase, that takes place in the physical space, right? That takes place in the coordinate space. But here, Bose-Einstein condensation is purely purely of quantum origin. Okay, so because here this happens even when you don't have any intermolecular forces. So remember that you are only dealing with ideal gases, so there is no intermolecular force involved between them, right? But even then you are getting this condensation. So this condensation is purely of quantum origin, and secondly, it takes place in the momentum space and not in the coordinate space. So these are the this in a way is very important to understand that Bose-Einstein condensation is way different from the normal condensation from one phase to another that we generally study in physical space. Okay. So now that means, when does Bose-Einstein condensation happen? So that can happen only when n is greater than Ne. Okay. So that is n is greater than this expression here. This is equal to Ne. Okay. Or now if you hold n and v as constant and vary T, so it happens when the temperature is lower than this critical temperature, which is given by this expression here, right? So that means when you go below a particular temperature, this effects can come in, where you have this probability of large number of particles coming to the zeroth energy state. Okay. So here Tc denotes the characteristic temperature that depends on the particle mass m and the particle density n by v. Okay. So accordingly, for T less than Tc, the system may be looked on as a mixture of two phases. Okay. So when T is less than Tc, okay. So what can happen is a normal phase, which consists of any number of particles distributed over the excited states. Okay. And then you have a condensed phase where you have n naught number of particles accumulated in the ground state. It's important to note this thing, that because n, you can see that if you look at the expression for Tc also, you'll see that it varies as n to the power 2/3, right? So accordingly, you have this dependence. So given your critical temperature or given some temperature, you can actually find the number of particles given Ne. Okay. So this dependence comes from this expression here. Okay. So that means for values for temperatures lower than the critical temperature, there are two phases. One phase where the particles are in the excited state. Another phase is a condensed phase, which is where the particles are accumulated in the ground state, which is epsilon equal to 0, right? So this is what is called the Bose-Einstein condensation. So if you look at the Ne by N plot or N naught by N plot, what you see here is that when T is equal to Tc, okay, beyond, so for values of T greater than Tc, you can see that Ne by N is equal to 1. That means all particles are in the excited state. Okay. But as you gradually lower the temperature below the critical temperature, you see that the values of number of particles in the excited state gradually decreases, while the number of particles in the ground state increases. Okay. And when T is tending towards 0, you can see that you have large number of particles in the ground state, and this is where the condensation happens. Okay. You can again look at the expression for Z. Okay, Z is the fugacity. Okay, and you will see that for values of V by lambda cube. So here V is the volume per particle. So it's given as V by N. Okay. Capital V, well, capital V is the volume and N is the number of particles. So capital V by capital N is given as small v. Okay. And if you look at the expression for Z, you would see that you can get this limit where Z gradually tends towards V by lambda cube inverse when you go towards the classical range. Okay. While on the other hand, when V by lambda cube tends towards 0, okay, you would see that Z is equal to 1 and Z remains 1 for values of V by lambda cube less than the critical value. Okay, this is the critical value. Below that, Z is always 1, right? So now this was your expression for P by KT. Okay, this was the expression that we had derived, right? What we will now do, we will see is that what happens for values of temperature less than the critical temperature and what happens beyond the critical temperature, right? Okay, just hold on for some. Okay, so now for T less than Tc, okay, what happens for T less than Tc? You know that the value of Z is 1 here, okay? So if you put the value of Z as 1, we had initially discussed that G is the Bose-Einstein function and that has an upper bound, okay? And that happens when Z is equal to 1 and that is represented as zeta of 5 by 2, okay? Because we have G of 5 by 2 Z. When Z becomes 1, this is represented as zeta of 5 by 2, right? So in a way, when T is less than Tc, you can replace the expression for pressure by this term here, right? And then this in a way tells you that this is proportional to T to the power 5 by 2, right? So you have to consider you have an extra T term here and you know that lambda goes as T to the power half, right? So accordingly, if you consider both, you would see that the pressure goes as T to the power 5 by 2, okay? And this is independent of V, which implies infinite compressibility, okay? Now what happens when T is equal to Tc? When T is equal to Tc, you can explicitly write the expression for lambda. Okay, this is what has been done here. So if you write the expression explicitly, you will have a Tc to the power 5 by 2 term. Okay, so it's the same term, it's the same expression, but here you have explicitly written lambda and lambda has temperature and you have replaced all the temperature in the expression by Tc, right? And this is what you get. So this is your pressure at the transition point. Okay, what happens for T greater than Tc? So for T greater than Tc, this is your expression, right? T by Kt is given as 1 by lambda cube G 5 by 2Z, right? And then if you remember the expression of N by V, from there you can replace 1 by lambda cube by N by V K, N by V G 3 by 2Z, right? So what has been done here is lambda cube has been replaced in terms of G 3 by 2Z, okay? So this comes from this expression here. If I go back, this comes from this expression here. Remember that when T is greater than Tc, your N minus N naught is equal to Ne and Ne is approximately equal to N. So you can write N by V equal to 1 by lambda cube G 3 by 2Z. So in a way, now you can replace lambda cube by N by V G 3 by 2Z, right? And this is what has been done here, right? So you have replaced 1 by lambda cube in terms of G 3 by 2Z, okay? And this is what you get, right? Where G 3 by 2Z is given by this expression, okay? Now, similarly, now if you look at the expression for the internal energy, this was your expression for the internal energy we had derived from the grand canonical partition function, right? Now what will we do? So again, for T less than Tc, you can find the specific heat, okay? Here what has been done is that, see, again for T less than Tc, so for T less than Tc, you can replace G 5 by 2 Z as zeta of 5 by 2, right? Because for values of temperature less than the critical temperature or the transition temperature, your Z is equal to 1, right? So, and then if you do that, you can again do a derivative of the internal energy to find the specific heat. And this is your expression that you get, right? So here again, if you consider the dependence of temperature, how lambda depends on temperature, you can say that Cv goes as T to the power 3 by 2. Okay. And at T equal to Tc, this is how you can replace it. Here again, they have replaced the values of, like explicitly replaced the values of temperature by the by the transition temperature or the critical temperature Tc. Okay. And then you get this expression, correct? So this is close to 1.925, which you can see is significantly higher than the classical value of 1.5. We know that in classical case, Cv is given as 3 by 2 nkt, right? Nk. So that means at the critical point, the specific heat is higher than the classical value. Okay. And then what happens for T greater than Tc? Again, here you can replace this lambda cube by in terms of G3 by 2Z, like we had done in the last case. And there you have to do this derivative with respect to temperature. Okay. So you have to, so in that case, we use this relations. Okay. And if you use this relation, you get this expression for the specific heat. Okay. So this is your expression for specific heat for T greater than Tc. And this is your expression when you are at the transition temperature or the critical temperature. And this is what happens when you go below the transition temperature, right? So if you plot them, you would get something like this. So when T is equal to Tc, you get a value of 1.925, which is greater than the classical value. Below that, Cv goes as T to the power 3 by 2, which comes from this expression here because you have this 1 by lambda cube dependence. Okay. And then as the temperature increases beyond the critical temperature, it gradually goes towards the classical value. So you can see that at temperatures much greater than the critical value, it would show values similar to the classical case. Okay. So now this is what we were discussing. Hello, Kamlesh.
Yes, ma'am.
Yes. So what we just discussed is that we discussed the different properties of Bose gas. Okay. So what happens at Bose-Einstein condensation? What is the mean occupation number? How does the fugacity change below the critical temperature and above the critical temperature, and all that derivations? You know all this, right?
Yes, ma'am.
Okay. And so can you tell me that we had solved for the density of states once, right? And there we had seen that so in 3D, the density of state goes as epsilon to the power half, right? Do you
Yes,
remember
ma'am.
that?
Yes, ma'am.
Okay. And then now if you have 2D, how will it change?
Ma'am, I think it's a constant.
Right. So it comes because initially for 3D, we take it as 4 pi p square dp, and then for 2D, it would be taken as 2 pi p dp, right? And then you replace p in terms of the given energy, right? Is it right? This is
Yes,
how
ma'am.
you do it, right? Okay. So because that, I just discussed this because it would be important in solving different questions because the density of states would differ depending on what dimensions you are in. Okay. Just for you
Okay.
to remember. Okay.
Yes.
So now this is a question. So here the Bose condensation occurs in liquid helium at this particular value. Okay. And it's said that the density of helium 4 is around is 1,000 times smaller than that of liquid helium. Okay. Gaseous helium 4 is 1,000 times smaller. So you have to say that at which temperature will Bose condensation occur in gaseous state. So can you tell me how to address this question?
I don't remember the expression for critical temperature.
Right. So see, this is what we had derived in the last few slides. So this is the expression for the critical temperature. Okay. So this comes from this expression here. So as you can see, T goes as N by V to the power 2/3, right? So N by V is the density. So that means T goes as density to the power 2 by 3. So if you use this relation, can you tell me what the answer would be?
Yes, ma'am. Ma'am, critical temperature is directly proportional to the density power 2 by 3, right?
Right.
So,
So now it's said that the density is 1,000 times smaller.
yes, ma'am. So that, ma'am, is it 217 Kelvin?
Huh? Who, which answer you're saying?
217 Kelvin?
See, it's
No,
smaller.
no, no. Yes, ma'am. Yes, ma'am. So,
1,000 times density is 1,000 times smaller, meaning the critical temperature would be 100 times smaller, right?
yes, ma'am.
1,000
So,
to the power 2/3.
0.0217 Kelvin.
Right. And that is equal to,
Uh,
change it to millikelvin.
yes, ma'am. 2.17 millikelvin.
0.0,
217.
0.0217 Kelvin. So
Yes,
now
ma'am.
if you want to change it to millikelvin, you will multiply by 1,000, right?
Yes, ma'am.
So it would be
2.17.
all right, 0.02, right? So it should be
21. Yes, ma'am. 21.7.
right. So the answer is B, correct?
Yes, ma'am.
Right. So this is how it goes. Okay. So just try to derive the equations once and then remember this kind of dependencies, like how does temperature depend, how does pressure depend on this density and this variables. Okay.
Yes,
Because
ma'am.
yeah, try to
Ma'am,
get used
here,
to.
ma'am, here psi 3 by 2 represent the gamma function.
No, it's not gamma function. So
Uh,
it's
zeta
it's
function.
the zeta function. So it's the,
Okay.
so you remember the Bose-Einstein function, right? G is the Bose-Einstein function. So if I go back 1 second, I'll show you the expression. So mm, so this is your Bose-Einstein function. Okay. So you had this integral and then you replace this integral by this function, which is actually a series of z, right? This is called Bose-Einstein function. Okay. And then what happens when you put z equal to 1? You would get a series like 1 plus 1 by 2 to the power gamma plus 1 by 3 to the power gamma, right? And that
Okay,
is
ma'am.
called the zeta function, right? So in a way, as you can see, g 3 by 2 for z equal to 1 is called zeta 3 by 2.
Okay, ma'am.
Okay. So so if you do the derivation, you'll see that this is how your TC goes. Okay. Okay, what the question book? Huh. So right, so once you derive the equation, you would see that it depends on density as 2/3. So remember this dependencies. Okay,
Yes,
the yeah, okay. So now this is another question. So you have a large number n of ideal bosons, each of mass m, and they are trapped in 3D potential, okay, given as half m omega square r square, right? The bosonic system is kept at temperature which is much less than the critical temperature. So the question asks how the chemical potential, so what condition does the chemical potential satisfy? So what will this be?
ma'am. The fugacity must less than 0, right? So,
Fugacity must be less than 0. Is it the case?
I don't know exactly,
Okay,
but
so what is the you can say what is the mean occupation number for Bose gas?
it runs from 0 to n.
No, no, mean occupation number. The expression for the mean occupation number. What you are saying is the value of Ni, or the number
Yes,
of particles in each energy state. But
yes, ma'am.
after using that, you find the mean occupation number, right?
Yes, ma'am.
For the different energy states. What is that expression?
Ma'am, Z inverse e power
Yes, 1 by
beta.
Z inverse e to the power beta E
It's
minus
okay.
1.
-1. Yes, ma'am.
Right. Now, for this to be, you can say finite, what should be the condition? Z inverse e to the power beta E should be
Less
greater
than.
than 1, right?
Yes, ma'am.
Greater,
Yes, ma'am.
greater than 1.
Okay, ma'am.
So wait, I'll show you the, I don't know where it is. It- Right. So if you look at this expression here, this is your, so this value, this is called the mean occupation number, right? And this is your expression. Now, for this to be finite, your z e to the power minus beta e should be less than 1. That means z inverse e to the power beta e is greater than 1, right?
Yes, ma'am.
Right. So if you use this relation and you know z is equal to e to the power mu by kt. So if you put z as e to the power mu by kt, what do you get? So replace z by e to the power mu by kt. You understanding, right? You would get a relation between the chemical potential and the
Potential and
energy.
energy. Yes, ma'am.
Right. What would be that relation?
Ma'am, mu must uh, less than epsilon.
Right. And what is epsilon? Epsilon means the energy
The energy.
states, right?
Yes,
Right. So that means mu should be less than all the different values of energies, right?
ma'am. From the ground state to all the state.
Right. So ground state is the minimum energy. So that
Yes, ma'am.
means if mu is less than the ground state, mu is less than all the energy states, right?
Yes, ma'am.
So this tells you that mu should be less than the ground state of your system,
Yes, ma'am.
right? Like for free particles, what happens is for free particles, the lowest energy is E equal to 0, right? Free particle meaning energy equal to P square by 2m. So when there is zero momentum, your energy is 0. And so the minimum energy possible is 0. So in that case,
Okay.
what would happen? Mu should be less than 0,
0.
right? Right. But now if we go back to our question, it was said that the particles were in a potential given as half m omega square r square, right?
Yes, ma'am.
So what will that mean then?
The ground
What would
state energy is 3 half h cross.
omega, right?
Yes, ma'am. 3 by 2
So
h
what
cross omega.
so what would be the answer then?
From
You just said the answer,
yes, ma'am. The upper bound is 3 half h cross, and
right? So which of the options matches with what you just said?
A and B.
How does B match? B says that mu is greater than 3 by 2 h cut omega, right?
Oh yes, ma'am. So it will be
Right,
A.
right. So that means given a system, you if you are asked about like this conditions, what the chemical potential satisfies or something like that, you have to use that idea that the chemical potential should be less than the ground state energy, right?
Okay, ma'am.
Yeah, okay. So now this is another question. So here this is typically a very numerical question. So I would share the solution with you because there's no point doing the entire calculation. But
Yes, ma'am.
so what's interesting for this question, what is important for you to understand is that photons are bosons. Okay, so that means how photons would be distributed in a given system would follow, they would follow the Bose-Einstein distribution, correct? So here you are asked that how many photons are there in 1 cc of radiation, okay, at some particular temperature. So what this tells you is that the number of photons per unit volume in the frequency interval nu to nu plus d nu is given by this expression here. Okay. And then if this is your density of states, like depend in the frequency interval, you can do an integration for all values of frequency, and that would give you the total number of photons per unit volume, right? And then you do a calculation, and this is what you get. This is the number of photons, and then this is the total radiation. So if you this is the formula for total radiation. It also comes from the Bose Einstein distribution. Okay, just as we find the total energy for the normal ideal Bose gas, similarly here this is the same expression, and then you do E by N, and then you get a value like that. But what important for solving these questions, or this kind of questions, is to remember how you get to this expression. Okay, so it's like this is the basic expression, right? For
Yes,
where
ma'am.
n epsilon is the number of particles in the in the region epsilon to epsilon plus d epsilon, and this is the density of states. This is again in
Oh,
3D. So you have v by h cube 4 pi p square dp into 2, because you can have the different angular spin angular degeneracy, right? So plus 1
ma'am.
or minus 1, and yeah,
Yes, ma'am.
tell me.
Ma'am, for the
Uh,
photons, we have
So the photons can be in plus
plus
1
one or
state or in minus 1 state, right?
okay,
And
ma'am.
so that
It
because of that
means
you get, yeah, you get a,
polarized in one direction or the other.
so this is the angular spin momentum. Okay,
Okay.
so
Okay.
that gives you plus 1 or minus 1. So because of that you get a 2. Okay, so that is 8 pi p square dp into v by h cube. Okay. Then you change from the momentum space to the frequency space, where you have used the relation that here the energy would be given as E equal to h nu, and we know that P is given as h nu by C, right?
Yes,
So
ma'am.
you do that, and then you go to the frequency space, and this is the density of states in the frequency space. Okay, now why do you set alpha equal to 0 for photons? Is because in a you can say, so what happens in a basic system is that, so photons can be absorbed, and photons of one particular energy can be absorbed, and photons of another energy can be released. So in a way the number of particles are not conserved here, right? So the alpha, or this constant alpha, which is equal to mu by kt. So how did we get that? If you remember long back in the in the derivation for the grand canonical ensemble, we had considered that summation over ni equal to n, right? And accordingly we had considered a Lagrange multiplier of alpha, and then we got some value for alpha. But for photons, you have to set alpha to be 0 because of this absorption and emission, which because of which the number of particles keep on changing. Okay, so if you put alpha equal to 0 in the expression, what you get is this value, right? So G nu is the density of states, G nu d nu, and then you have e to the power h nu by kt minus 1. So h nu is the energy, okay? And then you have to, so then you just replace the value of the density of states that you just found, and this is same as what has been written here. So it's important to remember how you use your basic concepts of ideal Bose gas or the Bose-Einstein distribution to physical systems like this, the Planck distribution for photons and all of this. Okay, the Planck's law. Okay,
Okay.
so so once you know that, you can use this. These are very standard ideas that if this is the number of photons per unit volume, what is the total number? You can just integrate over the entire frequency space, and then you get the total number. If the energy is specified, you can find the energy per unit photon. Right? These are very standard things, but what's important is to remember this physical understanding. Okay.
Yes, ma'am.
Yeah. Now, there's another question where it's said that we have an ideal Bose gas in d dimensions, okay, and it obeys a dispersion relation which is given as a k to the power s, where k is your momentum, okay, and a and s are constants. Now, for Bose-Einstein condensation to occur, the occupancy of excited states, which is given by this expression here, so this should remain finite even for mu equal to 0. And you are asked, when can this happen? So what could be the possible answer?
Ma'am, finite means the
So that means, so if you put mu equal to 0, you would get epsilon to the power d minus s by s dE by e to the power beta e minus 1, right? And
yes, ma'am.
then, so that the integral should be finite. So what happens, suppose you have limits from 0 to infinity, right? Now, if you put epsilon equal to 0, what happens? You get e to the power beta 0 minus 1. So it becomes 1 minus 1, right? So the denominator becomes 0,
Yes,
right?
ma'am.
So now, what
It
happens
will
here?
diverge.
Here also, you can, if epsilon is 0, you would get 0 by 0 form, right?
Yes,
So
ma'am.
in that case, if you remember how we used to solve limits, we used to, so in 0 by 0 form, we used to do derivatives, right? Like till we get a finite value of the system, of the limit, right?
Yes, ma'am.
So
Orbital
if you,
rule.
hmm,
Orbital rule.
right. So if
Yes,
you
ma'am.
do that, what will you get? You would get something like, so you have to do d minus s by s times the differentiations, right? And below also you would similarly do the differentiations. So for that to be finite, you would get something like d minus d by s minus 1 factorial kind of term in the front, right? So for that to be finite, d by s minus 1 should be greater than 0, right? Because
Yes, ma'am.
see, negative values of ne doesn't make any sense, right? Ne is the number, is a number of particles. So that means d by s minus 1 should be greater than 0.
One. Yes, ma'am.
So that means d by s should be greater than 1.
Zero. Must be a positive number.
Mhm.
Must be a
d
fast positive number.
d by s minus 1 should be a positive number. So that means d by s should be greater than 1, right?
Yes, ma'am.
So now you can also match with what we have done. So we know that Bose-Einstein condensation is possible in 3D. So consider that, so now your d is the number of dimensions. So d is equal to 3, okay? And then we know that for massive particles, where the particles do have considerable mass, we know that the density of state goes as epsilon to the power half, right? So if you put d minus s by s as half, right? What do you get? You get d by s to be 3 by 2, right?
Yes, ma'am.
And then if you have a massless particle, your G by E goes as E square. So if you again put that value, you would get d by s as 3. So in both cases, d by s is greater than 1. So whatever we were thinking is consistent, right? So for this question, the solution should be d by s greater than 1, right?
Yes, ma'am.
Okay, is it clear?
Yes, ma'am. Clear.
Okay. And then can you tell me why did we get this difference? Like why is G by so why is the density of state going as epsilon to the power half here and epsilon square here?
Ma'am, massless particles means photons.
Okay,
So the energy would be P times C.
right.
So that the density of states is given by 4 pi p square
Hmm.
dp.
Hmm.
So
So if you put the values there, you get
this
epsilon
is,
square.
yes, ma'am.
And what
Mm,
happens when you have, okay.
So the density of states would be 4 pi e square by c to the power 3 d epsilon. Ma'am, is
Right,
it right? Yes, ma'am.
right, right. So that means it goes as epsilon square, right?
Yes, yes, ma'am.
And then for materialistic particles, what is the relation between the energy and the momentum that we take?
Ma'am, materialistic particle.
Meaning massive particles. So particles which have mass. So how did we get epsilon to the power half here?
P square by 2m.
Is equal to energy, right? And then
Yes,
we do
ma'am.
the same process and then we get epsilon to the power half,
Yes, ma'am.
right? Right. So it's important to get used to this kind of things. So this was roughly what I was telling. So if you consider 4 pi p square dp, you can do a substitution and then you would get epsilon square and there you will have c cube in the denominator, right? This is what you were saying. It's correct.
Yes,
So you should get used to how things change when you have, so depending on your dispersion relation, right? So dispersion, this is a very general case for massive particles or particles with mass, your S is 2, right? And for massless particles, your S is 1. So because K here is momentum, okay? So this is a very general case, and then this is the different cases that can be possible. Okay.
ma'am. D is dimension and S here stands for.
S here stands for the power of momentum to which your energy depends,
Okay,
right?
ma'am.
Because if you look at, this is the dispersion relation. Dispersion relation is the relation between energy and momentum. K here is the momentum. Okay.
Yes, ma'am.
So you understand, right? For massive particles, it's p square by 2m, so S is 2. And for massless particles, it's p into c, so there S is 1, right?
Okay, ma'am.
Yeah. Okay. So now, understanding whatever we had discussed in the last question, it should be very straightforward to answer this. So here it said that you have an ideal Bose gas in 3 dimensions. So that means D is equal to 3 here. Okay. With the energy momentum relation given as epsilon proportional to P to the power S, right? And S is greater than 0. Now the range of S for which the system can undergo a Bose-Einstein condensation at non-zero temperature. So what should the value be then? So what was the condition for Bose-Einstein condensation we just saw?
Ma'am, D by S must be greater than 1.
Right. So what is the D value here?
Ma'am, 3.
Right. So what?
S is.
Huh,
Yes, S here is not specified but greater than 0.
Hmm.
So S must be less than 3.
Right.
So ma'am, is it C?
No, actually, it's one. It's
Oh, okay, ma'am.
because it's because we are looking at the integral values of s. Okay, so integral in the sense that 0 to 1 you would have some fractional values which we are not considering. So I have a confusion in the case that how to address this physically. But generally in the systems that we generally have this integral values, right, like p square p, or like physical in the physical cases. But so in a way you can have your values either 0 means it has no pressure, no momentum dependence. And then you can have a massless particle where it goes as p to the power 1, or you can have massive particles where it goes as p square. But uh, physically I don't know of a situation where it goes as a fraction. So in a way I don't know how to answer why why we are not considering between 0 and 1. I would look into it, but the answer is 1 because a because physically this is what is actually physically what happens. Okay, so basically it's true that you can get, one can get confused between c and a, but the answer is a because so we don't have this fractional dependence, which like for me I don't know about this fractional dependence.
Okay.
Okay, so the answer would be a. Now this is a continuation of the same question, that in which dimensions among 1D, 2D, and 3D is Bose-Einstein condensation possible for massive bosons and for massless bosons, right? Use the same relation that we just derived, that d by s is greater than 1, and tell me that for massive bosons, out of these three dimensions, where Bose-Einstein condensation can be possible. So for massive bosons, what is your value of s?
Ma'am, it is 2.
Right,
So D must be greater than 2.
right. So it should be in
In
3D,
3
right?
dimensions. Yes, ma'am.
Right. So that means for massive bosons, you can have Bose-Einstein condensation only in 3 dimension or beyond, right?
Yes,
But
ma'am.
then what happens for a massless boson?
Here S is 1. So D must be greater than 1. So
Hmm.
uh, 2D and 3D.
Right. So this is a very like physically this is very important to remember that for massive bosons you can have Bose-Einstein condensation only in 3D. Out of 1D, 2D, or 3D you can have only in 3D, while for massless bosons you can have Bose-Einstein condensation. So condensate can form even in 2D, right? Not in 1D, but in 2D it can be possible, which is not the case for massive bosons, right?
Okay, ma'am.
Yes, okay. So I think this is it. So do you have any doubt regarding this ideal Bose gas which you want me to explain?
Ma'am, I have a doubt.
Yes, tell me.
In the zeta function,
Okay.
actually, in one of the integral from 0 to infinity of
Like this the definition of the Bose-Einstein function.
yes, ma'am.
Okay. So what exactly is the is the doubt? So should I explain to you how we get this, or
Can you explain
okay?
the
So
in,
hmm, yeah, yeah. Tell me.
in the integral? How would you get the series?
Okay, so basically, this is your this comes from the grand canonical ensemble, right? This you
Yes,
know, right?
yes,
And then what? And this is how your n goes, okay? And here, this is your mean occupation number. So this is what we just discussed. Now, when you can consider that the spectrum of single particle states are continuous. So for large V, what you can do is you can change this summation to integration,
integral.
right?
Okay, ma'am.
And then that will be an integration over the phase space. And in the general case, we have not put the value of A yet. This is what the expression would look like, right? And then you can get, so this would go to 0. And then finally, this would be your expression for pressure, okay? Now for Bose gas, your A should be -1, right? So now, if you consider that the particle is a non-relativistic free particle, you know that epsilon is given as p square by 2m. So there, as we had discussed, we can find the density of states given by this expression here, right? And if you put that expression here, what will you get? You would get this expression for p by kt, right?
Yes,
Now
ma'am.
here, what we have done is that, see, this density of states tell you that when epsilon is equal to 0, your density of state goes to 0. That means there are no, so according to this relation, there are no particles in the zeroth state. But that is not actually true, right? You can have situations when you can have large number of particles in the zeroth state for bosons, right? So, so that means you have to explicitly consider the epsilon equal to 0 condition. So that's why what you have done is then you have taken the epsilon equal to 0 condition outside and you have written it explicitly outside the integral. Okay, that's why you have got this extra term, right? 1 by v ln 1 minus z, or 1 by v z by 1 minus z, right? You know,
Yes,
you
ma'am.
understand this, right? And now,
Okay.
no, like, do you understand? If
Yes,
you have
ma'am.
a doubt, you can ask me.
Integration by parts or
No, 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 no. We are not doing integration by parts. See, if, so initially, when we had, if you remember about the Fermi gas, what did we do? We had this density of states, and we had put the we have changed the summation to integration, and we have found the pressure, right? That's what we did for Fermi gases. But there is a difference between fermions and bosons, is that in bosons you can have large number of particles in one state. There is no limit over how many particles can be present in one state, right? So what this density of states is telling you is that when epsilon equal to 0, that is the zeroth energy state, your density of state is 0. But is it necessarily true? Not, no, right? You can have particles in the zeroth state. And we had seen that for the Bose-Einstein condensation, you can have large number of particles in the zeroth state, right? So it's
okay,
not
ma'am.
physically correct to ignore the epsilon equal to 0 term, right? So in a way, in the density of states, or when you are writing the expression for any thermodynamic parameter, you do have to consider the case when epsilon is equal to 0, right? So, but then if you put epsilon equal to 0 here, it goes to 0 because your density of states goes as epsilon to the power half. So how do you solve this? What you do is you take the epsilon equal to 0 case outside the integral. Okay.
Okay, ma'am.
So what happens when you put epsilon equal to 0? You get ln 1 minus z,
One
right?
minus z. Okay, ma'am.
Right. And then you have this 1 by v, which comes because you initially had pv by kt, right? And then you
Yes,
divided by v. Here there was an integration over the position coordinates. So v got cancelled. And here, because you have not done the integration, you have this 1 by v term here, right? You're just taking the epsilon equal to 0 case outside the integral. This is what you have done here. Similarly, you have done the same thing here, right?
yes, ma'am.
This is not
Okay.
integration by parts. Now it's clear, right? So now what you can do is look at this expression here, z by 1 minus z. What is z by 1 minus z physically, right? look at the expression for the mean occupation number. If you go back and look at the expression for the mean occupation number and put epsilon equal to 0, that is, you are in the zeroth state. So what is the value of the mean occupation number at the zeroth state? It's given as 1 by z inverse minus 1, right?
Yes, ma'am.
So you can write it as 1 by z minus 1. Take z to the numerator, you would get as z by
Is that
1 minus z,
1 minus h? Okay, ma'am.
right? So that means z by 1 minus z is the mean occupation number of the zeroth energy level, right?
Okay, ma'am.
So that means what you can now do is you can replace this z by 1 minus z term by n naught, where n naught is the number of particles in the zeroth
Ground.
state, ground state,
Oh,
right?
okay.
So then what you do is, this is your expression. This is the integral. So here what happens is you have this 1 by v ln 1 minus z term also. You can see here that as z increases, so as you go close to unity, the term z by 1 minus zv, which is this term, becomes very prominent. Okay, so you cannot ignore that. But ln 1 minus z by z goes to 0. Okay, so because of that, what you can do is you can write an expression for p by kt, which is given by this integral, right? And here what you have done is n naught by v, which was that 1 by v z by 1 minus z term, you have taken that in the left hand side, right? So in
Yes,
both the cases, in the right hand side, you have this integral. And then what you do, now you define a integral which is given by this expression here.
okay, ma'am.
So in a way, this integral can be written in terms of this Bose-Einstein function, which is given by this integral. So that's how this is being replaced here. And this integral, if you solve explicitly, you can, so this was from a book where in the appendix, it was given how you get finally this series. That's a very mathematically involved derivation. But
Okay.
so what it means is, if this is your integration, you can write it in terms of a function, which is called the Bose-Einstein function. And that is actually a series of z. Okay. And this is how it looks, right?
Okay.
Now, because it's a function of z, we know that z lies between 0 to 1, right? So that means your g nu of z is also bounded. It also has a maximum value. And when do you get that? You get that when z is equal to 1, right?
Yes, ma'am.
Right. So this is not important currently. So this is just using the partition. But now this is your expression for g nu. Okay. So now what you can do is, considering the case when z is equal to 1, you put z equal to 1, right? So that would give you a series like this, and that is called zeta of the corresponding new value, right?
Okay, ma'am.
This is a series. This is a series which is defined as zeta to 3 by 2, because for each values you have the power of 3 by 2, right? So this is important because now what happens for values less, so when the temperature is less than the critical temperature, right? In that case, z becomes 1, right? So in those cases, you can, so this is your normal definition of NE, right? Now what happens is, you can see that here what you have done, when n is greater than NE, like, should I go to the go through the entire derivation, or should I just tell you how, where we are using zeta? Do you know this thing?
Yes, ma'am. You can tell me where we use theta.
Right. So what is being done here is that this is your basic definition of basic expression for the number of particles in the excited state. Okay. But then when the total number of particles is greater than this number of particles in the excited state, the greatest bound, how do you find a bound for this term? This is your expression. You have this series here. Now, what is the upper bound of NE? The upper bound of NE is when G 3 by 2 Z has the upper bound, right? And that upper bound will happen when Z is equal to 1,
1.
right? And that
So
is called the zeta function,
theta 3 by 2. Okay.
right? So that means for whenever you reach the upper bound of NE, you would replace this term by the corresponding zeta function.
Okay.
That's what happens when your total number of particles is much greater or is greater than this upper bound. So when the number of particles are much greater than the upper bound, what happens is this is the maximum value of NE that you can get, right? For given a particular value of volume and temperature, this is the maximum value of Ne that you can get is the case when you replace this term by zeta 3 by 2.
Okay, ma'am. Ma'am, it is clear.
Okay.
Uh, can you go to the photon problem, the total number of uh, photons?
Total number of photons. This one?
Yes, ma'am.
Okay.
Ma'am, here the integral from 0 to infinity of x square by
Hmm.
ex minus 1.
Hmm.
Is it a standard integral or?
Yeah, I think they have solved it numerically. It's a difficult integral to solve. So that's why
Okay.
they have provided the value directly.
Okay.
It's a very mathematically involved integral. So generally, in most cases, you need to remember this. Like you don't need to remember. You can just like it's difficult to solve. Like because uh, I think that you have to do a number of steps. I
Okay, ma'am.
personally don't remember what substitution to do. But yeah, it's a mathematically involved integral.
Okay, ma'am.
Okay. Any more doubt?
No, ma'am.
Okay. So then let's call it a day. Okay.
Okay, ma'am. Thank you.
Yeah. Thank you. Thank you.
Hello.